Welcome to Professor Mad, Decoding Everyday Science.
The 4-day-long search for the missing Titan submersible has come to a tragic end. Reports have confirmed that the vessel was subject to a catastrophic implosion during its journey towards the shipwreck, which would have killed all 5 passengers instantly.
Let's try to understand what really happened to Titan. The ocean covers approximately 70.8% of the Earth, but more than 80% of the ocean remains unexplored. In some ways, it's a lot easier to send people into space than it is to send people to the bottom of the ocean. The intense pressures in the deep ocean make it an extremely difficult environment to explore. To comprehend the immense pressure at extreme depths, let's take a closer look at the underwater pressure equation. The pressure at a point located at a depth h from the water level is influenced by several factors, including atmospheric pressure, water density, gravitational constant, and the depth itself. The pressure at the considered point is equal to the atmospheric pressure plus the product of depth, water density, and gravitational constant. As the depth increases, so does the pressure. 40 meters is the depth limit for free diving. This limit is set to minimize the risk of nitrogen narcosis and decompression sickness, which can impair a driver's judgment and result in dangerous situations. Beyond a depth of 1,000 meters, known as the aphotic zone or midnight zone, sunlight cannot penetrate, creating perpetual darkness in this region of the ocean. At the depth where the Titanic rests, approximately 4,000 meters below sea level, the underwater pressure is incredibly high. However, OceanGate's Titan submersible stranded out as the only manned submersible capable of conducting commercial tours at this extreme depth. Let's try to calculate the pressure at this level. Atmospheric pressure at the sea level is about 100 kilopascals. The depth of water is about 4,000 meters. The density of water is about 1,000 kilograms per cubic meter. Let's assume the gravitational constant is 10. Now do the math. So the pressure near the Titanic wreckage is about 40 million pascals. That's nearly 400 times the atmospheric pressure at the surface. To help grasp the immense pressure, consider a cube with sides measuring 1 meter each. If we were to place a weight of 4 million kilograms on this cube, it would simulate the equivalent pressure experienced at that depth of the ocean. This amount of weight is comparable to the combined weight of approximately 8,000 average cars. Such a tremendous force exerted by the underwater environment at such extreme depths. But not from just one side like this. Underwater pressure envelops a submerged body from every side. Immense pressure surrounds every inch of a submerged vessel. Therefore, when designing a submersible to withstand extreme depths, the structure must indeed be super strong. Let's explore how this remarkable vessel was constructed to withstand the unforgiving forces of the deep sea. Measuring 22 feet in length and with a total height of approximately 8.3 feet, the Titan was a marvel of engineering. The Titan submersible was equipped with a sophisticated propulsion system consisting of 4 electric thrusters. 2 of these thrusters were dedicated to horizontal maneuverability, allowing the submersible to move laterally and navigate through the complex underwater terrain. The other 2 thrusters were utilized for vertical movement, enabling the Titan to ascend and descend in the water column with precision and control. This advanced propulsion system played a crucial role in ensuring the submersible's maneuverability and ability to explore the depths of the ocean effectively. We can separate this into 3 basic parts. Within the unmanned rear section, crucial elements such as oxygen tanks and vital electronics were stored. These components were essential for sustaining life and maintaining communication during the deep-sea expeditions. Landing frame provides stability and support during the submersible's descent and ascent, as well as when it rests on the ocean floor. The most critical aspect of the Titan was its inner hull, which was meticulously engineered to withstand the tremendous pressures encountered in the deep ocean. The inner hull consisted of 2 titanium hemispherical caps each end, providing exceptional strength and durability. The Titan's viewport is 7-inch thick plexiglass, acrylic, measuring 21 inches diameter. According to OceanGate, that's the biggest viewport of any deep-diving submersible. Connecting these hemispheres was a carbon fiber wound cylinder, boasting a diameter of 4.6 feet and a length of 8.3 feet. The walls were constructed with a thickness of 5 inches, composed of robust carbon fiber material. There are 667 layers of very thin carbon fiber in this 5-inch piece. With an empty interior cabin space, the OceanGate relied on a 5-inch thick outer shell for strength to withstand extreme pressures. However, this design approach has been regarded as a significant failure of the submersible, leading to the tragic loss. According to the Daily Mail, the Titan had been subjected to repeated stress over the course of more than a dozen previous dives. On each dive, the pressure on the hull increases with the depth and again decreases when it comes to surface. This has happened many times. Elongating the cabin space without any internal support increased the pressure loads on the midsections of the submersible, leading to increased fatigue and delamination loads. Increasing and decreasing pressure on a carbon fiber material repeatedly is like bending a wire back and forth many times. Carbon fiber layers begin to crack or fracture into layers, causing the hull to weaken. Each trip would put tiny cracks in the structure. This might be small and undetectable to start, but would soon become critical and produce rapid and uncontrollable growth. Now it is confirmed the vessel was subject to a catastrophic implosion at some point during its voyage towards the Titanic shipwreck. So, what does it mean for a submarine to have imploded? An implosion is the opposite of an explosion. When the force due to water pressure becomes larger than the hull can withstand, the vessel collapses violently inwards, causing an implosion. The collapse occurs at an astonishing speed, about 671 meters per second. During the implosion, the air inside the submersible, which has a high concentration of hydrocarbon vapors, auto-ignites, resulting in an explosion. The entire process happens within about a millisecond, leaving no chance for escape. According to experts, the individuals inside the submersible would not even realize that something was wrong before the vessel collapsed completely. It is a painless way to pass, albeit a tragic one. As we reflect on this tragic incident, it serves as a somber reminder of the incredible forces and risks involved in exploring the depths of our oceans. Our thoughts go out to the families and loved ones of the brave individuals lost in this unfortunate event. May they rest in peace. Like and subscribe us for more scientific explanation videos.